Welcome to lecture series on digital electronics under EPG Pathshala. This module is dedicated to understand one of the special type of ADCs, that is integrating ADCs. Under integrating ADCs, we will be talking about single slope and dual slope ADCs. Now, let us first identify the importance of ADCs in day to day life. The world around us is analog in nature. Whatever the parameter that we measure, those parameters are abundantly available in the analog form. But whenever we use smart gadgets or smart devices, we need to convert these analog parameters or analog signals like temperature, pressure, humidity, even voice is in the analog form, that must be converted into digital form before we store it or process it or send it anywhere. So, naturally we need some kind of analog to digital converter in the digital system or a smart gadget. So, we would be recording this analog signal through sampling, quantization and coding method. Now, these three techniques are already used in almost all analog to digital converters. We have already studied 4 different types of ADCs. The first type of ADC that we have studied is the flash ADC or simultaneous ADC, which is the fastest ADC of all. Then the second ADC that we have studied is a counter ramp type of ADC, where it involves comparator, a counter and ADC. So, naturally there is a closed loop feedback while comparing analog signal with a discrete value. Whenever we talk about these two ADCs, out of these two ADCs, the second ADC is the slowest one, that is counter ramp is the slowest one. Whenever we apply any new signal, the counter is always reset. So, it gives you some kind of a error in the measurement. That is why we think about a faster ADC, slightly faster than the counter ramp ADC. This ADC is known as tracking ADC. Once the signal is tracked to a desired value, it will go on continuously sending or converting the analog signal into digital and can be recorded anywhere. This is basically the tracking ADC. In addition to that, these two ADCs are feedback based. Similarly, we can use a successive approximation based ADC, which is relatively faster as compared to tracking ADC and counter ramp ADC. It requires simply 8 to 10 conversions, depends upon the number of bits. If I take 4 bits, so naturally I will hardly use 4 comparisons. If there are 16 bits in the ADC, there will be 16 comparisons. So, the conversion time is fixed. That is the most important advantage of successive approximation ADC. But when we talk about some stable or precise ADCs or the ADCs with high accuracy, then we will have to go to the integrating type of ADCs. Integrating ADC involves simple integrator in the construction. So, we will be talking about either single slope ADC, dual slope ADC or multi slope ADCs, which enhances the accuracy in the measurement. So, let us focus more on understanding the construction, working principle and applications of these ADCs in this module. Let us begin with the learning objectives. First, to understand the need of single slope and dual slope ADCs. Second, to study the basics of single slope ADC. Further, to learn the basic principles of dual slope ADC. Finally, to know the advantages and disadvantages of integrating ADCs. Let us first talk about the need of single slope and dual slope ADCs. There are various types of ADCs, each one with its strength and weaknesses. These ADCs can be classified according to the concept on which they are designed. So far, 4 popular ADCs were discussed in the previous modules. Flash ADC has a large volume of components like comparators in its architecture. In another ADC, a counter and ramp circuit using digital to analog converter DAC was also used in the conversion process. In the tracking as well as successive approximation ADC, it was not possible to avoid using a DAC in closed loop architecture. In such ADCs, the major components include DAC, analog comparator and some logic modules. In basic counting ADCs, it was observed that Much greater accuracy could be obtained using combination of integrating and counting methods of conversion. This provided a new way of conversion of analog into digital and led to the development of high accuracy single slope, dual slope or multi slope ADCs. This approach reduces the design complexity and improves the measurement quality by using dual slope integration concept. In slope or integrating type ADC, it is possible to avoid DAC and utilizes analog ramping circuit and a digital counter with precise timing in the construction. An integrating ADC is a type of ADC that converts an unknown analog input voltage to a digital representation by using simple op-amp based integrator. Such ADCs usually are slower because of time required for the integration. The speed of ADC can be improved by sacrificing the resolution. Although integrating architectures are not much popular, but they are still used in variety of precision applications such as digital voltmeters and digital multimeters. The basic idea behind slope or integrating ADC is to use operational amplifier based integrator circuits to generate sawtooth waveform. This simple ramp signal is then compared against the analog input by a comparator. The time it takes for the sawtooth waveform to exceed the input analog signal is measured by a digital counter clocked with precise square wave signal. Let us now discuss the internal architecture of single slope ADC. This ADC has 6 important blocks in the construction. The first block is an operational amplifier used as a comparator. The function of this comparator is to compare the voltages applied at the inverting and non-inverting inputs of the operational amplifier. AND gate is the second block of the ADC. One of the input of AND gate is the clock. The clock pulses will be passed to the output of AND gate only when the other input of AND gate is active high. The third important block of the ADC is the binary counter. This counter counts the applied clock pulse. Normally, up counter is used in the operation. Another important block of ADC is the latches. The function of latches is to lock and store the binary number. The next block in the architecture is the ramp generator. An operational amplifier based integrator circuit is used to generate a ramp or sawtooth waveform. The last block of the ADC is the control logic. It helps in controlling various blocks so as to complete the analog to digital conversion. Let us now discuss the interconnection of various blocks. The unknown analog input is applied to the non-inverting input of the comparator. Other input of the comparator is the ramp waveform generated by the ramp generator. It is applied to the inverting input of the comparator. The output of the comparator is connected to the input of AND. The comparator output is also connected to the control logic to take appropriate decision. The output of the comparator can be active high or low depending on its inputs. The AND gate output drives the clock input of the counter. If the AND gate is enabled, then the clock pulses will be passed to the clock input of the counter for counting. The outputs of the counter is the binary output. The outputs are labeled as Q7 as MSB, Q6, Q5, Q4, Q3, Q1 and Q0 as LSB. These outputs are connected to the D inputs of the latches. The latch can store the count only when the control logic generates the enable signal. The final digital value corresponding to analog input is taken from the output of the latches. Control logic also generates the reset signal to reset ramp generator so that output ramp voltage starts from 0 volt. Control logic also generates the clear signal to clear the count in the counter, so that counter can start counting upward from binary 0. Let us now discuss the working of single slope ADC. If the diagram is observed carefully, we can definitely say it is very similar to counter ramp ADC, as it uses counter, but instead of using DAC for generating step ramp, it uses a circuit called an integrator. Integrator is formed by using an operational amplifier, resistor and a capacitor. Integrator produces a sawtooth waveform on its output from 0 to maximum possible analog voltage sampled at that instant. In brief, the ramp generator produces a constant slope reference voltage. At the beginning of conversion cycle, the counter is reset and linear ramp generates output is 0 volt. At this point, the analog input is greater than the reference voltage generated by the ramp generator. Therefore, comparator produces a high output. This high state at the output of a comparator enables the AND gate. This allows the clock pulses to reach the clock input of the counter. Assume that the slope of the ramp is expressed as volts per millisecond. The ramp voltage increases with a constant slope with time. The comparator output remains in high state as long as the unknown analog input voltage is greater than the ramp voltage, that is V in greater than V ramp. This allows the clock to pass clock pulses through the gate to the counter for counting. As long as a ramp waveform starts, the counter starts counting from 0 to 2 raised to n, where n is a number of bits to be implemented. At certain stage, when the ramp voltage reaches the analog input value and crosses it, that is V in less than V ramp, this changes the state of the comparator to low state. This low state is also informed to the control logic. This low state also disables the AND gate, which stops the clock pulses from reaching to the counter. The control logic now generates the enable signal to store the binary count into the latches. This completes the cycle of analog to digital conversion. The control logic once again starts the conversion process by resetting the ramp generator to 0 volt and clearing the counter. In the overall conversion, it is necessary to keep track of the time. A graph of voltage against time is shown here. The ramp generator produces increasing ramp voltage with reference to time. It is the time the ramp generator takes to reach the value V in is indirectly indicated by counting each LSB per clock period. For the worst case, when V is equal to V ramp, it is necessary to wait for 2 raised to n clock periods for complete conversion. The time for conversion of analog to digital, which is referred as TC, is equal to V in upon LSB into T clock. A track of time it takes to reach the value V in by counting each LSB per clock period, that is T clock. As LSB change can be given by LSB is equal to V reference upon 2 raised to n. The conversion time is given by TC, that is equal to V in upon V reference into 2 raised to n into T clock. Assume that the slope of the ramp is 1 volt per millisecond. The analog input voltage is 2 volt and the clock frequency is 100 kilohertz. This indicates that the ramp will also reach at 2 volt, will run for 2 milliseconds. As the comparator output has been high for 2 milliseconds, 200 clock pulses have been allowed to pass the gate to the counter. The counter counts in binary values representing decimal 200. By using proper scaling and decoding, the number can be displayed as 2.00 volt. Let us talk about advantages of single slope ADC. First, single slope ADC do not require a DAC module, nor does it need the use of many comparators to do the conversion. Secondly, it provides simplicity in design and low cost to produce. Next, it enhances the reliability of conversion. This ADC guarantees the linearity of the conversion process, which leads to better quality. There are two major disadvantages. The main drawback of the single slope ADC is the slow conversion speed. The output can take as long as 2n clock cycles to convert single value. In dual slope ADC, the main component is integrator. The integrator generates two different ramps, one with analog input Vin and another with known reference voltage -V reference. Hence, it is called as dual slope ADC. The unknown analog input voltage is converted into time period measured by the counter. This is basically an indirect method of analog to digital conversion. Let us now understand the architecture of dual slope ADC. It consists of 7 main blocks as described here. The first block in the dual slope ADC is an integrator. It is an operational amplifier based circuit where non-inverting input is grounded and inverting input receives a resistor R and the output is fed to the inverting input through a capacitor C. The output voltage of the integrator is the integration of input voltage. The next block in ADC is a comparator. It compares the voltage at inverting input with that of non-inverting input. As non-inverting input is grounded, the comparator acts like a zero crossing detector. The output of the comparator can be either in high or low state. The comparator output drives one of the input of AND gate and the other input receives the clock. This AND gate allows the clock pulses to be passed only when the comparator output is high. These clock pulses passed through AND gate are counted by binary up counter. The output of the counter can be stored in the D latches after the conversion. The most important block is the control logic, which controls the overall operation of the converter. One of the inputs to the control logic is the comparator output. Control logic also receives another input from counter as the reset signal. It generates an enable signal for the latches to store the binary output of the counter after the conversion process is over. In addition, the control logic also provides a clear signal for the counter to clear the count before the commencement of the conversion process. Control logic also generates a switch control signal. This switch control signal allows the converter to connect either Vin or -V reference to the integrator. Let us now understand the operation of dual slope ADC. The operation of dual slope ADC is similar to that of single slope ADC, except that there are two ramps used. One of the ramps is single variable slope ramp and another one is a fixed slope ramp. A ramp generator is basically an integrator. It is used to produce the dual slope characteristics. Let us start with the assumption that the counter is reset and the output of integrator is 0. Now assume that a positive input voltage is applied to the input through the switch. The position of the switch is decided by control logic so that this input is applied to the inverting input of the integrator through a resistor R. As the non-inverting input is grounded, Then in this amplifier the inverting input is at virtual ground. Assuming that V in is constant for a period of time, there will be a constant current through the input resistor R, therefore through the capacitor C. Now C will charge linearly because the current is constant. As a result, now the integrator output generates a negative going linear voltage ramp. The output of the comparator is high. This enables the AND gate and the counter receives the clock pulses and counter starts up counting up to n. When the counter reaches a specified count n, which is based on fixed interval, then it will reset. A reset signal from the counter is applied to the control logic. The control logic generates a switch control signal to control the switch. This changes the switch position and negative reference voltage minus V reference is applied to the integrator. Now at this stage the capacitor is charged to negative voltage proportional to the input analog voltage. Now the capacitor discharges linearly due to constant current to minus V reference. This produces a positive going ramp at the integrator output starting from minus V with a constant slope that is independent of the charge voltage. As the inverting input of the comparator is still negative, the output of the comparator produces high state. This enables AND gate and the counter receives the clock pulses and counter starts up counting again. As the capacitor discharges, the counter advances its count. The time it takes the capacitor to discharge to 0 is dependent on the initial value of the voltage, which is proportional to V in. As soon as the integrator output voltage reaches 0, the comparator switches to low state and disables the clock to the counter through the AND gate. The low state at the output of the comparator allows the control logic to enable the latch storing the binary count. The binary count is proportional to V in. This completes one convergence cycle. In dual slope ADC, the integrator generates two different ramps, one with unknown analog input voltage V in and another with known reference voltage minus V reference. Hence it is called as dual slope ADC. The first negative going ramp continues to a fixed time period T1, which is determined by the counter. At the end of fixed time T1, the ramp output of the integrator is given by V0 is equal to minus V in upon RC into T1. As the slope of the ramp is depend on V in, hence for different voltages the ramp rate is variable as shown here. Similarly, when counter reaches a fixed count at time T1, the counter resets to 0 and switches the integrator input to the negative V reference. Now the ramp generator starts with the initial negative value of the output and increases in positive direction until it reaches 0 volt and the counter records the binary count. When the output of the integrator reaches 0 volt, the comparator output becomes negative, that is logic 0, and AND gate is deactivated. Hence no further clock is applied through AND gate. Now the conversion cycle is over. The positive ramp voltage is given by V0 is equal to V reference upon RC into T2. As V reference is constant, hence the slope of the ramp is fixed. Hence it is a fixed slope ramp. Thus dual slope ramp has one variable slope ramp and a fixed slope ramp. The amplitude of negative and positive ramp can be equated as follows: minus V in upon RC into T1 is equal to V reference upon RC into T2. cancelling RC, we get minus V in into T1 is equal to V reference into T2. Let us rearrange the terms so that we get T2 is equal to minus V in upon V reference into T1. As V reference and T1 are constant, the digital count obtained during T2 is dependent only on applied input voltage. Let us consider the clock frequency as 1 megahertz. The reference voltage is minus 1 volt and fixed time period T1 is 1 millisecond, and the RC time constant is also 1 millisecond. Assume that the unknown input voltage V in is equal to 3 volt. During the fixed time period T1, the integrator output V0 is given by V0 is equal to minus V in upon RC into T1. Therefore, V0 is equal to minus 3 upon 1 millisecond into 1 millisecond. Thus, we get V0 as minus 3 volt. During time period T2, the ramp generator will integrate from 0 volt. Then the period for counting will be given by T2 is equal to minus V in upon V reference into T1. Therefore, by substituting these values, we get T2 is equal to minus 3 upon minus 1 into 1 millisecond. Thus, we get 3000 microsecond. The counter will read it as 3000, and by activating decimal point using decoder, the display can read as 3.000 volt. Let us now discuss the advantages and disadvantages of dual slope ADC. The major advantages are: the analog to digital conversion result is insensitive to errors in component value. Second, there are very few adverse effects from noise, and third, it has high accuracy. The disadvantages are: due to dual integration process, the converter is slow. Second, the accuracy is dependent on use of precision external components. Third, due to various blocks, the converter is costly. Let us summarize few important points regarding this module. In this module, we have focused on two different types of ADCs. The first one is single slope ADC and the second one is a dual slope ADC. The major component of both the ADCs is the operational amplifier based integrator. This integrator can be used to generate either single slope or it can be used to generate two slopes. The first slope is always a fixed slope and the second one is a variable slope. Now, in single slope ADC, whenever the input voltage is applied, the input voltage is integrated and some fixed time is allowed, and we allow the clock to be passed to the counter, and counter converts whatever the input voltage that is present into digital value. Whenever we talk about dual slope ADCs, now the conversion time is not dependent upon whatever the analog input voltage that we are applying. So, there are two types of ramps those are used. Basically, the ramp generator is an operational amplifier based integrator circuit. The charging and discharging time of the capacitor that is used. Whenever we discharge the capacitor, it is always with reference to a reference voltage. So, naturally there is no question of a variable slope, there is always a fixed slope ramp that could be generated, and therefore, what we get is the output digital count is independent of whatever the input voltage that we apply. So, naturally the advantage of dual slope ADC is that it is error free, it is not dependent upon whether the input varies in between the recording or not. So, naturally once the input is sampled, it could be converted into digital one without any problem of error transitions and so on. Thank you.